In this video I'm going to talk about the normal stress and strain. We're going to take an idea about what is the meaning of normal stress and strain. So let's go and see more about it. Okay, let's close this and let's start with an introduction here. So first of all, we want to know that why we need the understanding of normal stress and normal strain in general, and what are the applications that we might encounter in our daily life that is related to this this normal stress and normal strain. The most fundamental concepts and mechanics of material are stresses and strain. What is the meaning of this? Whenever that we are talking about mechanics of materials in general, you're going to find that we are dealing with something that is related to forces, okay, and these forces are being applied on cross-sectional areas, okay. So we are going to find that the force that is being applied on cross-sectional area are going to make something called stresses, and under this stress or under these stresses we're going to find that the element is going to be changed in its shape, whether if we're talking about bar, for example, under tension. Let's assume that it is under tension. We're going to find that this bar is going to be changed under this tension or under this tensile force, and it is going to be deformed by some elongation from both sides, for example. Okay, so here this is what we are meaning by the strain, as I'm going to define it later. That is the amount of elongation with respect to the total length of the element before elongation. If we say it was L, for example, before elongation, and after elongation it comes to be like L plus delta L. So this small delta L from one side here over L, it is going to give us the strain, as I'm going to elaborate on it in this a little bit later. And the stress is going to be the force that is being applied, whether it is tensile force, as in our case here, or compressive force on the area itself. This bar, it has an area. As I said, it has an area, as you can see here. Okay, so this area is going to be, under, or is going to be stressed by the force being applied. So this fundamental concept of the force being applied on an area, and this force is going to reshape the original member, whether by stretching it out or by decreasing its length, by decreasing its cross-sectional area or increasing it. This is what we meant, or this is what we want to describe using the normal stress and normal strain. Okay, these concepts can be illustrated in their most elementary form by considering a prismatic bar subjected to axial forces. Prismatic here means that it is the cross section is constant. Okay, this is prismatic, means that the cross section is not changing through the length. For example, this is prismatic section. If I drew this section something like this, this is non-prismatic section. Okay, a prismatic bar is a straight structural member having the same cross section throughout its length. So this is an important issue. Why we are placing emphasis upon prismatic bar? Because we are dealing with cross-section always, so we need the cross-section to be constant, but here it is variable. So we are dealing with prismatic section. Let's clear everything. Okay, so this is the meaning of prismatic bar. Okay, it is a straight structural member having the same cross-section throughout its length, and an axial force is, whenever I say that axial force, it is a load directed along the axis of the member, resulting in either tension or compression in the bore, right? So let's have an example from our daily life. If we have an aircraft, for example, so if you look to the landing gear strut here, which is connecting the wheels with the body of the aircraft, you're going to find that this member is under compression, as I have mentioned before in previous video. And if you are going to look to another element that is under tension, and also it is prismatic, it is this towing bar. It is the towing bar. It is under tension, actually, that the towing, this towing car is going to pull the aircraft through this tow bar, and this tow bar is going to be under tensile stresses. Okay, so this is the concept, okay, the main concept of stress and strain as we can see in reality. Let's dig deeper and try to understand more about it. Okay, let's have an exposure on the prismatic bar in tension or under tension. Okay, if we look to this illustration that you can see here, okay, so as you can see here, we have a bar, and this bar is under tension. This bar is under tension. The force being applied is P from both sides. Okay, so prismatic, as I said, the cross section is uniform throughout its length. And if we look to this bar under the force that is being applied, we call this the free body diagram of a segment of a bar. Okay, a free body diagram of a segment of this bar. So this bar is going to be dealt with as, or we're going to take part of it and say that there is force being applied from both sides on this segment, right? So this is the free body diagram. Okay, if we look to this figure B, you're going to find that the length of the element is, okay, L. We call this the segment of the bar before loading. So there is no loading here. This is the segment of the bar before loading. And after that, if you look to figure C, after we apply the load P and P from both sides, you're going to find that if we have, we call this the segment of the bar after loading. So after loading, as you can see here, the load is being applied, and you are going to find, that the length of this segment is increased. It is not L as before. It becomes L plus delta, right? Okay, so here there is something changed from this state or figure B to figure C, that under the tensile force there is an increase in the length of the member. Okay, and after that in figure D we are going to describe something new for us, which we call it the normal stresses in the bar. What is the meaning of the normal stresses? We are going to look at one segment here at the bar, which is MN, and we are going to cut here at this point. So we are going to find MN here, and to the right of it we are going to find that the force being applied, it is a concentrated force, but actually this concentrated force, which we can see it here, is going to be distributed around the cross section. So as you can see it here, okay, many arrows here. This means that the force is being applied uniformly over the cross section. When we divide P, the force being applied, to A or over A, P over A, this is going to give us what we call it sigma. Okay, this is what we call it sigma, or the normal stress. Okay, we disregard the weight of the bar itself. Whenever that we were, or when we were talking here, actually we were disregarding the weight of the bar. Disregarded, do not think about it. It's like as if it's massless. Okay, just the force is the only straining action that is going to be applied on the element. And assume that the only active forces are the axial forces P at the ends, as I have mentioned. At the right hand end of this free body, which is section MN, as I said here, we show the action of the removed part of the bar. As I said, when we remove this part, so here this is the action of the removed part, as you can see it here. That is the part to the right section MN upon the part that remains. Okay, as you can see it here. Let's clean everything. Okay, this action consists of continuously distributed, look to this word, continuously distributed stresses. What is the meaning of this? Let's go to the word continuously. Continuously means that at every point, the same normal stress applies, right? So at every point, this is the meaning of continuously. Distributed, because as we said, the force is concentrated, but when it is going to be attached to the member, it is going to be exactly distributed. Okay, so this is an important issue that you need to remember. And it is stresses. As I said, the stress means that it is force over, exactly, force over area, the area of the cross section itself. Okay, and the axial force P acting at the cross section is the resultant, take care of this word, resultant of those stresses. So we have many, like the stresses is continuous, the stress is continuous, and in the same time every point on the cross section is being stressed. The summation, okay, of these stresses across the entire cross section is going to give us the resultant, which is P, which is the force being applied. The resultant force is shown with a dashed line. This is the resultant force here. Okay, I hope that you have understood the meaning of the meaning of normal stresses and the prismatic bar, and how we can understand the continuity of the normal stresses along the member. Okay, let's go and dig deeper into the meaning of the stress and understand more about it. For the stress, it has units of force per unit area, force per unit area, and is denoted by the Greek letter sigma. Okay, as you can see here, this is sigma, and it equals to P over delta, P over A, where P it is the force, A it is the area of the cross section. Okay, so the units that we are expecting is force units over area units. In general, the stresses sigma acting on a plane surface may be uniform throughout the area, or may vary in intensity from one point to another. Okay, this is actually something that is we need to keep in our mind. I'm going to give some hints about it later after that. But in general, sigma that is acting on a plane surface, commonly it is uniform. Okay, commonly it is uniform. We are going to assume or presume that the force is acting upon the whole area in a uniform way. Sometimes maybe the force is not going to be acting on the area uniformly. For example, if we have something like this, and the force being applied not in the centroid, it is here. So we are expecting that this part is going to be under stress or going to be stressed more than this part. Okay, but commonly we are assuming that the center of the force, if we have the centroid of the geometry or the member, coincides with the center of application of the force being applied. Okay, so keep this in your mind. Okay, normal stresses may be either tensile or compressive, tension or compression, that's right. When a sign convention for normal stress is required, it is customary to define tensile stresses as positive and compressive stresses as negative. That's very common. Whenever we're talking about positive stresses, this means that tensile. Whenever we are talking about negative stresses, this means that it is compressive. Okay, that's it. And we said that the units are going to be, I'm going to talk about the units later on, force per unit area. So we are having like United States customary units, and we have the international units, as I'm going to show in the next slide. So we have US CU, which is the United States customary units. We are having, commonly we use pounds per square inch, and it is going to be PSI, or kilopounds per square inch, and commonly denoted as KSI. And for System International units, which is we use Newton for indication of force. So it is for Newton, it is going to be, this is the force units over meters squared, which is the area. Okay, and this is going to be Pascal. This is going to be Pascal, denoted as PA. Sometimes the Pascal is very small unit of stress, and we need to have some magnitudes of it, multiples of it. So we're going to multiply it by 10 to the power 3, which is like 1000. We call it kilonewton per meter squared, and this is going to be kilopascal, and or multiply by 10 to the power 6, which is meganewton per meter squared, and this is going to be megapascal, MPa. And if you look to the meganewton over meter squared, we can say that it equals to Newton over millimeter squared. Newton over millimeter squared. As you can see here, meganewton means that 10 to the power 6 multiplied by Newton. Okay, so here we are going to say, well, we are going to keep Newton as it is, and this meter squared we're going to convert it to millimeter. So we are going to multiply the numerator by 10 raised to the power 6, which means that Newton over millimeter squared, it gives us megapascal. So in short, Newton per millimeter squared means megapascal, and meganewton per meter squared also means megapascal. Okay, I hope that you are not confused for the units in general, whether for the US customary units or System International units. Okay, now let's go to the next. Note, a little note here, that axial force P acts through the centroid of the cross-sectional area. The stress is uniform distributed over the cross-section of the bar. What is the meaning of this? Actually, in reality, you are going to find that the force being transmitted to the main body of the frame or main body of the member through something like this. Okay, the bar end. Okay, it is a hinge here, like an I bar. Okay, this is what we call it, I bar. Okay, so this I bar is going to be the way or the means through which the force is being transmitted to the main bar body. We are expecting that here, for example, we are going to expect there is some stress concentration. There is stress concentration here. However, this stress concentration is going to be smoothly transmitted to the bar after certain length here. This length we found it to be B, which is the as you can see here, it is the depth of the bar itself. Okay, so we can say that there is a concentration that is going to happen near the ends of the bar, but this stress concentration is going to be uniformly distributed, okay, across the section itself, okay, after certain length from the end. This certain length we found it to be B. Okay, so the stress distribution in the steel eye bar is uniform at distances B or greater from the enlarged ends. Some stress concentration may occur at the ends, and we, as I said to you, there are stress concentration might occur here. Okay. Okay, so even when the stress is not uniformly distributed, the equation, which is sigma equal to P over delta A, may still be useful because it gives the average normal stress on the cross section. Okay, so still we are dealing with the same concept, which is the action of the force that is being applied over the cross-sectional area. If we say that there is some parts are not going to have uniform distribution, okay, but still when we say P over A, where A it is the cross-sectional area, it is going to give us average stress, which is going to be useful for us. Okay. Okay, now let's go to the normal strain. The elongation per unit length, or strain, we call it strain, is denoted by the Greek letter epsilon. Okay, there's no and here. It is denoted by the Greek letter epsilon. So it is like, as you can see, epsilon equals to delta over L. Delta over L. Okay, let's go back here. What is delta and what is L? Do you remember this? We said this is delta here, and do you remember this? This is the original length of the member itself. This is what we call it, the original length of the member. Okay, delta over L. Okay, if the bar is in tension, the strain is called tensile strain, representing an elongation or stretching of the material. If the bar is in compression, the strain is a compressive strain and the bar shortens. Okay, and we have mentioned this before. Tensile strain is usually taken as positive, it's the sign convention, and compressive strain is as negative. The strain epsilon is called a normal strain. Why? What is the reason for this? Because it is associated with normal stresses. So whenever we say normal strain, it means that it is associated with normal stresses. Okay, because normal strain is the ratio of two lengths, it is dimensionless quantity. As you can see, this is length unit and this is length unit also. So epsilon is dimensionless, it's only number, that is, has no units. Therefore, strain is expressed simply as a number, independent of any system of units. Okay. In practice, the original units of D and L, D here means that which is this delta, okay? This is the delta. D and L are sometimes attached to the strain itself, and then the strain is recorded in forms such as millimeter per meter. Sometimes even that millimeter per meter, it is also considered to be dimensionless, but we need to feel the this epsilon, so we want to put some units there. So we are going to put, for example, 6 millimeter per meter, means that every 1 meter there is stretching of 6 millimeter. That's the meaning of millimeter per meter, or inch per inch. Okay, in 1 inch, how much is going to be how much this part or this member is going to lengthen. Okay, so this is the way that we are expressing this normal strain. Okay, there is something else called uniaxial stress and strain, and whenever we say uniaxial, it has something that should always link to. The state of stress and strain is called uniaxial stress and strain if the deformation of the bore be uniform throughout its volume. If the deformation, that's the issue here, the deformation, okay, the deformation of the bore itself be uniform throughout its volume, which in turn requires that three things or three conditions here. The first one, the bore is prismatic, should be prismatic. You now understand what is the meaning of prismatic. The cross section is uniform. The loads act through the centroids of the cross sections. The loads act through the centroids. What is the meaning of this? If we have a cross section like this and it has the centroid here, the force must act here. Okay, we cannot say that the force is here, for example. This would not be uniaxial stress. There would be some bending stresses going to occur here. Okay, the material be homogeneous. This is the third condition, the material be homogeneous. I think that you know what is the meaning of homogeneous material, that is the same throughout all the parts of the bore. It is the same throughout all the parts of the bore. Okay, so this is the meaning of the uniaxial material. This is the meaning of uniaxial material. Okay, now let's go to the next part. Let's see here. Okay. Okay, so I think that it's enough for this video that is showing all the things that is related to normal stress and normal strain. I'm going to make a quick recap of what I have said. We mentioned about the real life examples of elements that we can encounter that is having compression or tension, and where that normal stress and strain applies. After that I talked about the prismatic bore in tension, and I mentioned about the free body diagram and how we can get a meaningful or an understanding of the normal stresses on a prismatic bore, and then I talked about the equation, the famous equation of stresses or normal stress, which is P over A, the force being applied over A, and we said that there is a relation, or there is units that should be used, force per unit area in general, and we said that there is sign convention that should be used as well. The sign convention is related to the negative if it's compressive normal stresses, and positive if it's tensile normal stresses. And after that we mentioned about the most customary units used, whether it is for the United States or for the System International. PSI and KSI is the most commonly used for United States. For System International we use Pascal, which originally means Newton per meter squared, or megapascal, for example, which means Newton per millimeter squared or meganewton per meter squared. After that we mentioned after that we mentioned about the stress concentration, how the force is being applied and transformed from the end of the bar to the main body of the bar, and we said that there is some stress concentration here, but we said that it's going to be uniform after distance of B, where B is the depth of the bar. And we ended with the normal strain, where that we call it epsilon, which means that the delta, which is the part of the length that is going to be increased over the original member length. And after that we said that there is something called uniaxial stress and strain, and we mentioned three main conditions. Of them is being prismatic element, loads should be applied on the centroids, and the material should be homogeneous. Thank you for listening, and I hope to see you in the next video.